Here we're going to be talking about solving systems of equations using graphing. There's other ways to solve them, but right now we're just going to be talking about solving a system of equations just using a graph. And that can be on the calculator. It depends on how the equation is written. It might be easier to actually graph it yourself, or it might be easier to do it on the calculator. Before we get into that, I just want to do the warm-up, which is just showing how we can graph from each of the three different forms that we learned about. We have slope-intercept, point-slope, and standard form, and we can graph pretty easily from each of them using different strategies. On the first one, which is slope-intercept, what we're given is directly in the name. We have the slope, and we have the y-intercept. So we're going to start by graphing the y-intercept. That's at -4. Y-intercept of -4. And the slope is 1/2, or it's rising 1 and running 2. Rising 1, going up 1, and running to the right 2 spots. So that's the next point on the line. I went up 1/2. I'm going to do that one more time. Up 1 and over 2. Those are the 3 points that I need for my line. Now I'm just going to connect those dots using my arrow there. It goes on in both directions forever. That's why I have arrows at the end of each set. The next one is point-slope. And again, it's directly in the name what I'm given. I'm given a point, which here it's really -5 and +4, and the slope, which is -3/2, which means I'm going down 3 and right 2. So I'm going to start at my point, -5, 4, and then use that slope, down 3/2, down 3 to the right 2. I'm going to do that one more time, down 3 and to the right 2, and I'll connect my dots one more time using an arrow. That's my second one. The third one is given in standard form. Actually, let me go back to the instructions. Linear equation, I just want to stress that again. Linear equation just means it's going to form a line. That's all we're dealing with right now, just graphs that form lines, straight lines. So, this is, again, standard form. From this one, the easiest way to graph, you could rearrange this into slope-intercept if you wanted to. If that's how you want to do that, that's fine. I think the easiest way to graph this is just using the x and y intercepts. So the x-intercept is when y equals 0. So that's the equation to find my x-intercept. I'm basically setting the whole y term equal to 0, and then solving for my x. 0 plus 4, -4x is just -4x. And then to solve for x, I'm going to divide by -4. That gives me -3. So my x-intercept is -3. To find my y-intercept, I'm going to do the exact opposite. I'm going to set the x term equal to 0, and then solve for the y. 3y plus 0 is just 3y. And then to solve for y, I'm going to divide by 3. So my y-intercept is 4. That is that. And then again, I'm just going to connect my dots using that double-ended arrow. So those are the graphs from slope-intercept, point-slope, and standard form. And I think those are the easiest ways to do that. There's definitely other ways. If you wanted to change the point-slope form or the standard form into slope-intercept and then graph from that, if you're more comfortable looking at it from the y-intercept and the slope, that's fine. Really, there's a bunch of different ways that you could graph this. Actually, last year and probably the year before, you even learned how to make a table where you plugged in x values, 0, 1, and 2, and then found the y values. You can do that on any of these equations also. You can plug in any x value that you want, find the y value that goes with that, and then graph those order cubes. So you should be familiar with all of that. The only thing that we're doing now is using these equations, or lines, in systems of equations. And a system of equations is really just two or more equations. Instead of just dealing with one equation at a time, we're going to be dealing with more than one equation. And there's going to be more than one variable. Two or more variables. That part's not new. We've had two or more variables in all of these equations. We've had an x and a y. That's going to stay the same. We just have more than one equation to deal with. When we're solving an equation, when we're solving a system of equations, when we're looking for the solution to a system of equations, it's finding the point or points, could hit more than once, where these two lines intersect. And when you think of a street intersection, we're thinking about where those two streets are crossing. So where these two lines cross, that's the solution of the system of equations. The system of equations is just looking for a point where these two lines hit each other. So we're going to look at this example where we're talking about these alligators' weights, and we want to know, when do these two alligators weigh the same amount? So they say that alligator 1 has an initial weight of 3 pounds, and it grows 2 pounds per month. Alligator 2 has an initial weight of 6 pounds, and grows 1 pound per month. So we're going to try to come up with equations for those. So for just looking at alligator 2, they start out with 6 pounds. So I'm going to say that y is the weight of our alligator, and x is the number of months. You could switch that, but the reason I set it up like that is because the weight is dependent on the number of months. The months is the independent variable, which is why I'm calling that the x. The weight is dependent, so I'm calling that the y. So I'm going to say y, my weight, is 6 plus 1 times the number of months. It's gaining 1 each month, or per month. So I'm multiplying that 1 times that number of months, which is my x. And I start out with 6, so 6 plus whatever I'm gaining each month. For the first alligator, it's similar. I'm going to rewrite this in the opposite order just to show you it doesn't actually matter what order. It's growing 2 pounds per month, so 2 pounds per month, plus the initial weight of 3. Those are both in slope-intercept form. They're the same thing. But it doesn't really matter which order we write that in, because addition is commutative. Now I'm going to graph these two. So I'm going to start off with that first one. I have a y-intercept of 3 and a slope of 2. That's really a slope of 2 over 1. So I'm going to start out at 3, 2, 3. I'm going to start at 3. And I'm going to go up 2, so I'm going to fill in these axes first. Don't think I'll have to go higher than that. I'm going to start at 3 and go up 2 each time. And then I'm just going to connect my dots. This one has a circle at the end of it. I don't know if you noticed that, but this actually has a dot at the end of it because we can't have a negative weight. That doesn't really make any sense. Or we can't have a negative time, excuse me. That would be a negative time. That doesn't make any sense. So it actually has a dot at the end of it. Most of the time we'll see arrows at the end of each of these. But when we're dealing with a context like an alligator's weight, we actually have to think about what does the axes really mean. If I go back to the left here, that's talking about a negative time, which doesn't make any sense. All right, for the second one, starting at 6, that's my y-intercept, and using a slope of 1. So I'm starting at 6. Using a slope of 1 means I'm just going up 1 each time. Let me connect my dots one more time. But you should have seen it as I was plotting those points. We have an intersection right there. Those two lines cross at that point. That looks like the coordinates 3, 9. That's where these points intersect. That's the whole thing I'm looking for with a system of equations. Where do my two lines hit each other? What does that point mean? So a point of 3, 9 is talking about 3 for the time and 9 for the weight. So at 3 months, both of these alligators weigh that same amount. Both alligators weigh 9 pounds. 3 months, they weigh 9 pounds. Both of the alligators are meeting at that point. That's what it means. This alligator started at 6, and he's growing slower. He gets up to 9 pounds after 3 months. This one grows a little bit faster, but they still get to 9 pounds after 3 months. I want to check to make sure that that point actually works in both these equations. So I'm using the point 3, 9, and I'm going to plug it into both of my equations. Y equals 2x plus 3, and y equals 6 plus 1x. I'm just going to plug in the x and make sure I get 9 for my y. So 2 times 3 plus 3. 2 times 3 is 6. Plus 3, I know that's 9, so that one's good. And then I'm plugging 3 in to that second x. So 6 plus 1 times 3, 6 plus 1 times 3 is just 3. We got 6 plus 3 again, that equals 9 also. That's just to confirm that it actually is a part of that equation and that equation, which really confirms that it's a solution to the system of equations. It's on both of those lines. That's where they have to be. All right. So there's a bunch of different, there's 3 different types of solutions when you're graphing systems of equations. You can have one solution where the 2 lines intersect at just one point, which is what we just saw. So the coordinates satisfy both the equations, but it's just hitting one time. So I'm going to draw that random line, and it hits this other random line just at that one spot. We could have infinite solutions. Which means that the 2 lines coincide. Actually, you can kind of see the word coincidence in there. Coincidence is just when 2 things line up, 2 things happen at the same time. That's what coincide really means. They're happening at the same time, and they are actually the same exact line. So I'm going to draw 2 different lines here. That one, and there's going to be a second line that goes right over top of that. Those are supposed to line up perfectly. That has an infinite number of solutions because they intersect an infinite number of times at every single point along this line. Those points have solutions. They're the same line, which means that they intersect an infinite number of times. And the final one is no solution. That's when 2 lines are parallel, because that means they never meet. These 2 lines will never hit each other. I'm going to try to sketch parallel lines. It's not going to be perfect. Remember, they need to have the same slope. Those have the same slope, different y-intercepts, so they just go off in the same direction. They keep the same distance between them the whole time, and they never actually meet. So there's no solution to that system of equations, because that's what we're looking for. Where those 2 lines meet, well, they're never going to meet, so there's no solution to that. So when we're graphing, we always want to check using the coordinates. So we're just walking through these 3 steps. First off, we're going to graph both of these equations on the same coordinate plane. Then we're going to use the find the coordinates of the point of intersection, and write that answer as an ordered pair. Then we're going to check the coordinates algebraically by plugging them back in. You can plug them into both equations to make sure that it's actually on both of those lines. All right. So we're going to try to graph these two first. I'm going to use my slope-intercept form here, using the intercept of 3 and a slope of -4/3. That's a rise of -4. I'm going down 4 and over 3 spots. My second one has a y-intercept of -4 and a slope of 1, which is really a rise of 1 and a run of 1. So I'm going up 1 each time. And you can see right there we have our intersection. I'm going to draw my lines in there, but we actually already found everything that we needed. The coordinates at that spot are my solution. I'm going to write that as an ordered pair. That's the point 3, -1. I'm just looking at the coordinates of that spot where they hit each other. Now I'm going to check to make sure that that actually is on both these lines. So I'm going to plug in 3 for x, so -4/3 times 3 plus 3, and I hope that equals -1. -4/3 times 3 is -4 plus 3. That equals -1, so that one's good. And then one more time, plug in 3, that second equation, 3 minus 4, that's also -1. So that is a solution to both the equations, and it's a solution to the system of equations. Next one is given in standard form. So again, if you want to rewrite that in slope-intercept, if that's easier for you to graph, that's fine. I'm going to graph it straight from standard form by finding the x and y intercepts. So for the first equation, I'm going to set y equal to 0 to find my x-intercept. That basically just goes away, so x is -4. That's my x-intercept for the first equation. My y-intercept, I'm going to do the same thing. I'm going to skip one step here. I'm basically just imagining that x term going away. When I'm trying to find my y-intercept, I set x equal to 0. So all I'm going to do is write this without the x term. So I have -4y equals -4. That basically means that y is just 1. So that's a second point on the line. I can graph a third one if I really wanted to. I can see my slope is going up 1 over 4. So I know that's going to be the third point on there. Now, I'll connect those dots now. Oops. Now I'm going to draw my second line. So 4x equals 8. This is to find my x-intercept. All I did was cross out that y term. So x is 2. My x-intercept for the second equation is 2. And my y-intercept, -4. Basically here I'm just crossing out the x term now. -4 equals 8. So my y is -2. My y-intercept there is -2. Actually, I can see my slope here again. It's going up 1 and over 1 each time. So I can graph a third point if I want to. And if I follow that, actually, I probably don't want to just sketch that line. I really want to count out my slope from here. So I'm going to go up 1 over 1 each time and find that that is my intersection. You actually want to graph the points. Don't just sketch the line and then try to guess where they're going to end up. I'm just finding my slope from here. It's going up 1 over 4, so it continues that up 1 over 4. That's how I got that extra point. For the second line, I'm just going up 1 over 1 each time. So my coordinates for my solution are, let's go in black again, 4, 2. That's the solution to the system of equations. From there, I just want to plug that in just to make sure that it actually is the solution. And it actually is on both these lines. I'm going to do 4 minus 4 times 2. 4 times 2 is 8. So 4 minus 8, that is -4. So I did that right. And for the second equation, I have 4 times 4. I'm going to do it up here. 4 times 4 minus 4 times 2. 4 times 4 is 16. 4 times 2 is 8. And 16 minus 8, that is 8. So it is on both those lines. Okay, you might have already picked up on this. We can actually do some of this in the calculator. If it's given in slope-intercept form, you can use the calculator to do this. Bring my calculator up. I'm going to shoot this down. Oh, don't do that. Okay, so if I want to, I can do this very easily in the calculator as long as these are actually in slope-intercept form. On this first one, they are. So I'm going to start off just by going to y equals and typing in my equation. I'm going to type in 2x minus 2. And as my second equation, I'm going to type in 5x. I want to figure out where these two hit each other. Okay, actually, before I even get into that, the reason I'm doing this on this example, if I graph these two, a y-intercept of -2, a slope of 2, going up 2 every time. This has a y-intercept of 0, and it's going up 5 each time. So those are my lines, and unfortunately, they don't meet at a whole number. That's really the whole reason why on this one, I need to use the calculator. Sometimes you will need to use the calculator or a different method. We're going to learn about some other methods to solve these. But sometimes you need to use the calculator because they don't meet at whole number points. So I'm typing those into y equals here. And I can graph them, but that's not that helpful because that gives me the same picture that I just found. And I could try zooming in, I guess. But that's not really going to be that helpful either because it's still going to show me that those are hitting in between these whole numbers. So I'm going to zoom back to zoom standard just to give me my original picture. And now I'm actually going to have the calculator find my intersection for me. You're going to hit second and trace, second and calc. It's that button. And the word intersect is right there for us, number 5. You can hit number 5, or you can scroll down and hit enter over number 5. It says first curve, second curve, and then a guess. The first curve and second curve are just asking if it's going to hit more than once. Our lines are not hitting more than once. So we don't actually need that. We're just going to hit enter, enter, and enter. And it's going to tell us exactly where those points hit each other. That's hitting at an x value of -0.6 repeating and a y value of -3.3 repeating. I'm going to rewrite those as fractions. You don't have to do this. I'm seeing my solutions as -2/3. If you want to write these as decimals, you can. And -10/3. That's my solution to the system of equations. I think you guys know how to check it at this point. I want you to check it on your own right now, but I'm not going to go through that. I'm going to go over to the next one, and we see that that's in point slope form and standard form. We can't graph that on the calculator. Not like it is at least right now, but we can change those around so that we can graph those on the calculator. On the first equation, I'm going to distribute first. That gives me y minus 3 equals -2x plus 6. And then I'm going to move the 3 over by adding it, so I get y equals -2x plus 9. So this equation isn't even going to go on that line. I have a y-intercept of 9 somewhere up there, and then a slope of -2. That's not going to make it on our line, or sorry, on our graph. This is another reason why we will have to do some of these on the calculator. It's just not practical to graph some of these. On the second one, I still need to change that into slope-intercept, so I'm going to add the 2x to both sides. I want to get y by itself, so I'm going to cancel out the -2x. That gives me -3y equals, I'm going to put the 2x in front, 2x plus 6, and then I divide by -3 on both sides. dividing that negative 3 into everything. So I have 2 over negative 3 times x, and then 6 divided by negative 3 is negative 2. I have my two equations now. Now I can actually type those into the calculator. I'm going to go back to y equals and type those two equations. So negative 2x plus 9, and scroll down. I'm going to put that negative up at the top. Negative 2 divided by 3x minus 2. I've got my two equations in there. I can graph them, but that's not really that helpful because those are meeting off at a point that I don't really want to have to graph, and it might be a decimal. Now I can hit second and calc, or second and trace. Scroll down to 5, and that will tell me my intersection. I'm going to hit enter 1, 2, 3 times, and that tells me my intersection. These two lines intersect at 8.25, comma, negative 7.5. Again, you can check those just by plugging them back in. Really, you want to make sure that you type that equation in carefully and that you solve for the equations carefully, because there could have been a mistake just getting to these equations. If you type that back in, or if you plug that back in, you're basically confirming that you did everything correctly there. Plug it back into the original equations when you do that. Use these two equations when you plug them in.